Hello students, in the previous sessions we discussed about differential equations, order and degree of differential equations, also about the particular and general solutions to differential equations. Here in this session we shall study about the formation of a differential equation whose general solution is given. We know that the equation x square plus y square plus 2x minus 4y plus 4 is equal to 0 represents a circle having center at -1, 2 and radius 1 unit. Differentiating with respect to x, we get dy upon dx is equal to x plus 1 upon 2 minus y, where y is not equal to 2, which is a differential equation. You will find later on that this equation represents the family of circles and one member of the family is the circle given in equation 1, that is x square plus y square plus 2x minus 4y plus 4 is equal to 0. Let us consider the equation x square plus y square is equal to r square. By giving different values to r, we get different members of the family. For example, x square plus y square is equal to 1, x square plus y square is equal to 4, x square plus y square is equal to 9. Thus, equation x square plus y square is equal to r square represents a family of concentric circles centered at the origin and having different radii. We are interested in finding a differential equation that is satisfied by each member of the family. The differential equation must be free from r because r is different for different members of the family. The equation is obtained by differentiating the equation x square plus y square is equal to r square with respect to x, that is 2x plus 2y into dy by dx is equal to 0 or x plus y into dy by dx is equal to 0, which represents the family of concentric circles. Here you can see in the figure the family of concentric circles. The inner circle is of equation x square plus y square is equal to 1 and this circle is of equation x square plus y square is equal to 4. Similarly, the outer circle is of equation x square plus y square is equal to 9. Now, let us consider the equation y is equal to mx plus c. By giving different values to the parameter m and c, we get different members of the family. For example, y is equal to x when m is equal to 1 and c is equal to 0. Y is equal to root 3 into x when m is equal to root 3 and c is equal to 0. Y is equal to x plus 1 when m is equal to 1 and c is equal to 1. Similarly, y is equal to minus x when m is equal to minus 1 and c is equal to 0. And y is equal to minus x minus 1 when m is equal to minus 1 and c is equal to minus 1. Thus, equation 1 represents the family of straight lines where m and c are parameters. We are now interested in finding a differential equation that is satisfied by each member of the family. Further, the equation must be free from m and c because m and c are different for different members of the family. This is obtained by differentiating equation 1 with respect to x. Successively, we get dy upon dx is equal to m and d square y upon dx square is equal to 0. This equation represents the family of straight lines from equation 1. Here you can see in the figure family of straight lines. This line is of equation y is equal to x. Similarly, this line is for equation y is equal to minus x and this is for y is equal to minus x minus 1, so on. Now, let us discuss about the procedure to form a differential equation that will represent a given family of curves. In the first case, if the given family f1 of curves depends on only one parameter, then it is represented by the equation of the form f1 x y a is equal to 0. For example, the family of parabolas y square is equal to ax can be represented by an equation of the form f x y a, that is y square is equal to ax. Differentiating this equation with respect to x, we get an equation involving y dash y x and a, that is g of x y y dash a is equal to 0. The required differential equation is then obtained by eliminating a from equation 1, 2 and we get f of x y y dash is equal to 0. In the second case, if the family f2 of curves depends on the parameters say a and b, then it is represented by an equation of the form f2 x y a b is equal to 0. Differentiating this equation with respect to x, we get g of x y y dash a b is equal to 0, but it is not possible to eliminate two parameters a and b from the two equations, and so we need a third equation. This equation is obtained by differentiating equation 5 with respect to x to obtain a relation of the form h of x y y dash y double dash a b is equal to 0. This is equation 6. The required differential equation is then obtained by eliminating a and b from equation 4, 5 and 6 as f of x y y dash y double dash is equal to 0. This is equation 7. Please note that the order of the differential equation representing a family of curves is same as the number of arbitrary constants present in the equation corresponding to the family of curves. Now, let us discuss some examples. Form the differential equation representing a family of curves y is equal to mx, where m is a arbitrary constant. For the solution, we have y is equal to mx. This is the first equation. Differentiating both sides with respect to x, we get dy upon dx is equal to m. Substituting the value of m in equation 1, we get y is equal to dy upon dx into x, or x dy upon dx minus y is equal to 0, which is free from the parameter m, and hence this is the required differential equation. Another example here, form the differential equation representing the family of curves y is equal to a sin x plus b, where a and b are arbitrary constants. For the solution, we have y is equal to a into sin x plus b. Take this as equation number 1. Differentiating both the sides of this equation with respect to x successively, we get dy upon dx is equal to a into cos x plus b. This is equation 2. Now, again differentiating this equation, we get d square y upon dx square is equal to minus a into sin x plus b. This is equation number 3. Now, eliminating a and b from equation 1, 2 and 3, we get d square y upon dx square plus y is equal to 0, which is free from arbitrary constants a and b, and hence this is the required differential equation. Another different example here, form the differential equation representing the family of parabolas having vertex at origin and axis along positive direction of x axis. See the solution. Let P denote the family of parabolas and let a comma 0 be the focus of a member of the given family, where a is an arbitrary constant. Therefore, equation of family P is y square is equal to 4ax. Take this as equation 1. Now, differentiating both sides of this equation with respect to x, we get 2y into dy by dx is equal to 4a. Take this as equation 2. Substituting the value of 4a from equation 2 in equation 1, we get y square is equal to 2y into dy by dx into x, or y square minus 2xy into dy by dx is equal to 0, which is the differential equation of the given family of parabolas. Here in this figure, you can see family of parabolas having the vertex at the origin and focus as a 0. Another example here, form the differential equation representing the family of curves given by x minus a whole square plus 2y square is equal to a square, where a is an arbitrary constant. For the solution, given that x minus a whole square plus 2y square is equal to a square, take this as equation 1. This implies x square minus 2ax plus 2y square is equal to 0. This is equation number 2. Differentiating with respect to x, we have 2x minus 2a plus 4y into dy by dx is equal to 0. That gives a is equal to x plus 2y into dy by dx. Put this value of a in equation 2, we have x square plus 2y square minus 2x into x plus 2y into dy by dx is equal to 0. That implies x square plus 2y square minus 2x square minus 4xy into dy by dx is equal to 0. This implies 4xy into dy by dx is equal to 2y square minus x square, which is the required differential equation. Here is an important example because it has more than 2 arbitrary constants. Find the differential equation of the family of curves y is equal to ae to the power 3x plus be to the power 5x plus ce to the power 7x, where a, b and c are arbitrary constants. For the solution, we are given that y is equal to ae to the power 3x plus be to the power 5x plus ce to the power 7x. Take this as equation number 1. Differentiating with respect to x, we have y1 is equal to 3ae to the power 3x plus 5be to the power 5x plus 7ce to the power 7x. Take this as equation number 2. Multiplying equation 1 by 7 and subtracting equation 2 from it, we have 7y minus y1 is equal to 4a e to the power 3x plus 2b e to the power 5x. Take this as equation number 3. Again differentiating with respect to x, we have 7y1 minus y2 is equal to 12a e to the power 3x plus 10b e to the power 5x. Take this equation as 4th. Multiplying equation 3 by 5 and subtracting equation 4 from it, we have 35y minus 12y1 plus y2 is equal to 8a e to the power 3x. Take this as equation number 5. Again differentiating with respect to x, we have 35y1 minus 12y2 plus y3 is equal to 24a e to the power 3x. This is equation number 6. Multiplying equation 5 by 3 and subtracting equation 6 from it, we have 105y minus 71y1 plus 15y2 minus y3 is equal to 0. That implies y3 minus 15y2 plus 71y1 minus 105y is equal to 0, which is the required differential equation. Now children, it is time to take the home assignment problems. Please note down question number 1. In y is equal to e to the power x into a cos x plus b sin x, form the differential equation by eliminating arbitrary constants a and b. Question number 2. Form the differential equation of the family of circles touching the y axis at origin. Question number 3. Form the differential equation of the family of parabolas at origin and axis along positive y axis. Thank you.